Hey folks, Mrs. White here, coming at you with our last new lesson for the year. Today we're going to look at solving exponential equations. The previous lesson to today, we were looking at exponential equations, but we were looking at what they look like when they're graphed and where do they come from. So today we're going to move into solving. We're going to start off today by looking at graphing again. So we're going to look at graphing one exponential function, and specifically we're going to be looking at exponential decay. Then we'll hop into some new stuff. So we'll spend some time looking at solving. We'll do two together and develop steps, and then you can try two on your own. We'll look at writing an equation from a word problem. So when we think about bacteria multiplying or cells multiplying, that's the type of situation where we'd have to write our exponential function. We're also going to look at another way exponential functions are used in the real world, which is with interest. So whether you're being charged interest for a loan that you have, or if you're earning interest because you have some sort of savings account through the bank, they might be using this formula. There's two formulas they could use. This is the one that would be compounding over certain periods of time. Your homework tonight is in the ebook. It's 9 through 15 and 20 through 23. So 9 through 14 is going to focus on solving. 15 is going to be probably the trickiest problem of them all. It's going to be one of these ones where you have to write it directly from a word problem. And then from 20 to 23, those are going to have you looking at calculating compound interest. Okay? So the due date for this homework is a little different. Normally our homeworks are due Tuesday before midnight. This assignment's going to be due Wednesday before midnight. I know some of you may or may not be watching this on Monday. If you headed out of your house a little bit, maybe spent some time with your family, maybe on Memorial Day you didn't actually take a look at this video. So if you're watching it on Tuesday, that's perfectly fine. Your homework's not going to be due until Wednesday. Okay, so take the extra day if you need it. If not, feel free to turn it in right on the normal time. In addition to that, there's a screenshot of this homework up. I want to be really clear with you. I did not make a mistake. I attached a picture that has the answers because I know often those word problems can be tricky and I know you like to skip them. So don't skip them, for one. For two, you got to show your work. And for three, feel good about your answer when you get it and it matches the answers that I've posted. Okay, I wanted you to see the key because I want you to know that you're doing it correctly. And if you're not doing it correctly, please, please, please attend office hours and ask some questions. I'm happy to do all those word problems with you folks. Okay? There's also a note-taking guide if you go to Classroom. You're welcome to print that out if you have access to a printer. Don't feel like you have to, but it does have all of the word problems already on it and all of the problems we're going to go over together in our lesson today. So let's do a quick little review of what was covered last class. And this is like the gnarliest exponential graph you're going to see. Okay, there's not going to be anything much more horrible than this. So I did mention before that it is an exponential decay function. And I want you to take a second in your head and think about how can I identify just from the way the equation looks that it's exponential decay versus exponential growth. Hopefully you're thinking about this little hot number right here, which is either our growth factor or our decay factor. And so when we look at this value, it's often referred to as our b, right? It's the base that holds up our exponent. If that value is between 0 and 1, then it's going to be decay, okay? And if it's greater than 1, it's going to represent growth. And this is kind of what we multiply by every time. That's what we're raising to whatever power. So that's really kind of like our multiplication factor. If we're multiplying by a fraction less than 1, but greater than 0, it's going to be getting smaller. Okay? So I notice it's decay. I notice I got something going on here. I have a coefficient I'm multiplying by here, and I have this being added on at the end. And this piece is really important because this plus 8 lets us know that our asymptote is going to be shifted up 8. So an exponential decay function usually looks like it goes really steep and then flattens out, and then it gets really close to an asymptote right on the x-axis. Okay, well here, whenever we add or subtract on the outside, remember that's a vertical shift and it's going to be exactly what you think. This one's going to be up 8. So I'm going to go up 1, 2, 3, 4, 5, 6, 7, 8, and the new asymptote will be there, and my whole graph should be shifted up. So just kind of a mental thought about this. This is how you tell where your asymptote has relocated, by the plus or minus on the end. Then, just like I had to do with square root graphs in our previous chapter, okay, I'm going to look at creating an XY chart, and I'm going to need 3 values for my x. And I'm going to look specifically at my exponent, which is x plus 5. And I'm going to set that equal to -1. I'm going to set that equal to 0, and then I'm going to set that equal to +1. And this is going to give me the 3 easiest exponents to handle. So I'm going to minus 5, minus 5. These are same sign, add and keep. So my first x is going to be negative 6. Minus 5, minus 5, I'm going to get negative 5. And then minus 5, minus 5, I'm going to get a negative 4. These are my 3 x's I'm going to plug in and get out my y's. So let's start off by plugging in negative 6 right here. Negative 6 plus 5 gives me a negative 1. So I currently have 1/2 times 1/5 to the negative 1 plus 8. Now, hopefully from our last lesson, but also from previous work, you remember a negative exponent means change the location. So this 1's going to become part of the denominator, and the 5's going to become the numerator. So it's really like 1/2 times 5 plus 8. Now, because I'm doing next after exponents, I would multiply and then add, subtract last. So I'm going to multiply these. I'll put it over 1. I get 5/2 plus 8. And then hopefully you realize, folks, that 5/2, 5 divided by 2 is 2.5, and 2.5 plus 8 is 10.5. So my first coordinate pair is left negative 6, up 10.5. My next point is where I plug in a negative 5 up here. So negative 5 plus 5 is 0. So I currently have 1/2 times 1/5 raised to the 0 power plus 8. I hope you're like, Mrs. White, we don't really have to write 1/5 to the 0 because anything to the 0 power is the same thing as 1. And 1/2 times 1 is just 1/2. And then our plus 8, which gives us 8.5 or 8.5. So I'll go to the left 5 and then up 8.5. Now let's see our last point here. I'm going to plug in a negative 4. Negative 4 plus 5 is positive 1. So I have 1/2 times 1/5 to the first power plus 8. Now, anything to the first is just itself. So I can kind of ignore that 1 and just go across the top, across the bottom. And I get 1/10 plus 8. And I literally told you what this is as a decimal, right? It's 1/10. So my answer is going to be 8.1 or 8 and 1/10. So for this point, I'll go over to the left, negative 4, and then I will go up 8.1. Now I'm ready to graph. So looking at these, my x's are all negative, so I only need to include the negative part of my graph, and my y's are all positive, so I really only need to include this first quadrant right here. I'm going to start by writing my asymptote, which we shifted vertically up 8. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to model an asymptote with a dotted line. Now remember, our graph is going to get really, really, really close to that line, but it actually can never touch it because it's an asymptote. I added a few more there. I'm going to have to go out to at least negative 6 here. So 1, 2, 3, 4, 5, 6. And I'm ready to plot my points. So I'm going to go over negative 6, up 10.5. So here's 8, 9, 10.5. Next point, I'm going to go over to negative 5, and I'm going to go up to 8.5. So here's 8 where my asymptote is. I'm only going to go up half a box. And then my third point helps me to continue to model this curve. I'm going to go over to negative 4, which is here, and up to 8.1. So just barely over that asymptote. And you can see, wow, this was a little bit steeper, and now it's evening out. Remember, as we sketch this, we do not want to sketch this curve going below the asymptote. Okay? And there's our graph, or our general graph, of this exponential decay function, right? So now that we've kind of taken a look at that, let's push forward with some new stuff. So if you have that note-taking guide, then feel free to look right at it right now, and we'll get right started. So first things first, you're always asked to solve equations, right? You've been asked that since middle school, but you have to recognize what type of equation we're dealing with so that you can pick a strategy to solve. So when you had a power of 2, those were always quadratics, right? When we had x squared. Well, now when you have an equation, which means it has an equal sign, and you have your x as an exponent, that's letting you know you're dealing with an exponential equation, okay? And there's several ways you can solve this. For our purposes, since we're pushed right up to the end of the year, we're only going to see problems that are going to be in these specific forms. So what I want you to think about for a second is these two bases, okay? So right now I have 2 raised to a power, and I have 8 raised to a power. And it's really tricky to compare those because they don't have the exact same bases. If this was 2 to some power and this was a 2 to some power, then I know those powers would have to be equivalent, okay? Now, I technically could do 8 times itself 3 times, get that really big number. and figure out how many times 2 fits into that number, and that would give me this exponent. Totally could do that, and that would work when you have an exponent on one side with a variable. But if you were taking on a problem like this second one here, where we have an x in this exponent and in the other one, now you're talking about it getting a little bit too tricky, okay? So coming over to this one, the first thing we're going to do is we're going to try to make our bases look the same. Now 2 cannot be simplified to anything because 2 is a prime number. We're going to take a look over at this 8, and what we're going to do is we're going to break that 8 into its prime factorization, which means we're going to factor tree it until it's all prime numbers. So 8 is divisible by 2 and 4. And 4 is divisible by 2 and 2, and those are all primes. So we could say that 8 is the exact same thing as 2 to the 1, 2, 3, 2 to the third power, right? 2 times 2 times 2, 2 to the third. Now I notice this base and this base are going to be the same, which means there's something cool we're going to be able to do in a second. So I'm going to bring down my 2 to the x power. I'm going to take out this 8, and instead of 8, I'm going to put in there 2 to the 3rd, excuse me. And 2 to the 3rd, like we just discussed, is the exact same thing as 8. So I just replaced this with this. Now this 3 is on the outside. I still have to put it on the outside of my parentheses because it was attached to the 8. Now hopefully you're like, oh, Mrs. White, this looks funky, but it looks familiar, right? This is one of our exponent rules. When we have an exponent raised to another exponent, we should multiply, okay? And that's the power to power rule. So I technically have 2x equals 2 to the 3 times 3, which is 9. Now, if you take a quick look at this, folks, 2 to the x has to equal 2 to the 9th. We already know what x has to equal, right? In order for this to equal this, x has to equal 9. Well, that's going to work every time you have the same bases. You're going to be able to just cancel them out and do exponent equals exponent. Now, in this case, that's our answer, right? We're done. But in this case, when we do exponent equals exponent, it's going to be a little bit more complicated. So this is as easy as they're possibly going to get. Let's develop some steps to talk about what we did here, and then we'll use those steps to solve our second one, okay? So the first thing we did here is you identified that it was exponential, okay? You're going to have to do that every time with every type of equation always. That's not really a step for solving. Once you've identified that, yes, I have a variable in the exponent, I need to figure that out, what you're going to do is you're going to take each base and you're going to find its prime factorization. Now, for all the examples you're going to be seeing, they're all going to factor nicely and the bases will match, okay? So you want it to get your bases to match. Now, once you've done that, that's this step right here. The second step you need to double check for is your power to power rule, okay? And remember, when you have an exponent raised to another exponent, you need to multiply them together, all right? After you've simplified that exponent by multiplying them using the power of powers rule, okay, we're going to cancel our bases because they're exactly the same. And then you can set it up as exponent equals exponent. Now, we didn't have to in this case, okay, but we might need to do some work to isolate our variable after that, and that would be our last step. So let's take a look at the second one now. I notice that these two bases are not the same and that my variables in my exponents. So I want to get those two bases the same by factoring both of them so that they have the same base. Now 3 is prime, I cannot factor it, but 9 is not prime. If I think of the factor tree for 9, it's 3 and 3, right? Or I could say 9 is equivalent to 3 squared. So I'm going to rewrite this. It's going to be 3 squared in parentheses raised to the 2x minus 1. Over here I have 3 to the 6x. So at this point now, I've done my prime factorization. If I take a look here and here, my bases match, which is rockin', right? I've completed my first step. Now I need to simplify any power of a power rule. So I'm going to look over here. I have 2, and then on the outside I have a 2x minus 1. So what I need to do is I need to distribute this 2 to both pieces, right? I have to multiply them, and to multiply a mono times a binomial, I need to distribute. So I end up with 3 to the 2 times 2x is 4x, and then 2 times minus 1 is minus 2. And this side stayed the same. There was no power raised to this outside of it. Now I've simplified my power to power. I have just the same bases. I'm ready to cancel those two bases and write it as exponent equals exponent. And now at this point, folks, I hope you're like, oh my gosh, I see it. It's going to be nice and quick to solve. I'm going to minus 4x and minus 4x. I have negative 2 equals 2x. Last step, divide 2. I get x equals negative 1. Okay, so I isolated my variable as that last couple steps there. So these actually are not atrocious. All the ones that I have for you are going to be reasonable. So your first step, and here we only had to look at one base. You might have to look at both. Okay, you're going to prime factorize both your bases, or at least one of them, to make sure that they match. Simplify your power to power rule. Cancel your bases and set your equation as exponent equals exponent, because in order for them to be equal, right, they have to have the same exponents. And then isolate your variable so that you can find your solution. Below, I have two problems for you. I'm already showing you the answer, so feel free to pause the video right now and give it a go. I'm going to quietly put up my work, and then I'll talk you through both of them at the same time. All right, folks, let's come together now. So I put up my work for both of these. If you got them both right, you can feel free to skip this little section. I'm just going to go over it. So first things first over here, I noticed neither of these were prime. So I took my 4 and I knew it was the same thing as 2 squared. So once I rewrote this as 2 squared, I said, okay, 64 is going to have a base of 2. So I divided it by 2 over and over again. I know 8 times 8 is 64, but I thought by pulling out the 2's, it'd make it easier for me to figure out 2 to the 6th. Okay, so once I did that, I simplified my power to a power rule by distributing this 2 to both pieces. I canceled my bases, set it as exponent equals exponent, plus 2, divide 4, I get n equals 2. On my next one, I noticed 5 was prime, but 125 isn't, so I factored it over here and got that it's 5 to the 3rd. So I rewrote it as 5 to the 3rd with an x plus 2 on the outside. I did my power to power rule by distributing that 3. I canceled my bases, set it equal to the exponents, subtracted 3x to get 2x, divided by 2, and I got x equals 3. So this is the first 6 problems in your homework are going to be problems like this. So take your time and do your best. The next problem you're going to come across is going to be a word problem like this, and this is probably the hardest problem you're going to see from your homework. Pretty much in this unit, right? Because we're only going to cover these 2 sections. This is our last new learning for the year. So Kristen starts an experiment, and there's 7,500 bacteria cells at the beginning. After 4 hours, there are 23,000 cells. So that more than doubled, but it didn't, and it more than, maybe it tripled, I don't know, but it did a lot, right? It went up. So there's definitely some growth that happened in those 4 hours. So you're asked to write an exponential function that could be used to model the number of bacteria after X hours if the number of bacteria changes at the same rate. So when they say rate here, they're not talking about slope because it's exponential, and the slope changes, right? It starts out slow and then it gets really steep. So our slope starts out small and then it gets very, very big. Okay, so it's not that we're going to do like y2 minus y1 over x2 minus x1. To figure out the rate, we're going to have to figure out our growth factor. So if you think back to our zombie video yesterday, we were introduced to y equals ab to the x. And this is the general form of an exponential function. So you have your y on the outside, which y is always on the outside. It's your dependent variable. It's what happens as the outcome. Your a is what you start out with. Your b is going to be your growth or decay factor. And then x is just x, it's what you plug in. And here they're telling us that x is going to be hours. Okay, they tell us that right here. So they actually gave us a bunch of information. They told us we started with 7,500, which is going to be our a. They told us 4 hours have passed, that's our x. And then they told us we ended with 23,000. So this 23,000 doesn't have to do with what it's growing by, right? We didn't say anything about the rate or growth factor. They said we ended with it, meaning that it's going to be our y value. So we're going to start off with that. So we're going to plug in what we know. We know it ended with 23,000. We know it started with 7,500. We do not know the growth rate, but we do know there was 4 hours. Now remember, this x is only attached to the b. If it was attached to both, there'd be parentheses, and there's no parentheses. So now, in order to get our growth rate so that we can write our general form of our function, which will look like this, okay, I need to calculate this b. I'm going to try to get it alone and positive. So I'm going to start by dividing by 7,500 on both sides. So let's see, I got to have a calculator somewhere is going on here. Let's do this. Here we go. So we're going to do 23,000 divided by 7,500. Wow, we end up with a big decimal. We're going to round it to 3.06, and then this will round up to the 7. So 3.067. So now we need to keep getting our b alone. And hopefully you have an idea of how to get rid of this fourth power, right? The inverse operation to an exponent is a radical, right? It's a root sign. So to get rid of a fourth power, we're going to fourth root. And over here, we're going to fourth root. That cancels. Now my b is totally alone and positive, and it's going to equal the fourth root of 3.067. Now that's not 3.067 divided by 4, right? It's a fourth root. So let's go and figure it out. We're going to do 3.067. We're going to press this little button, and we're going to fourth root it. And we're going to get 1.323, and that's going to be the decimal we stick with, okay? 1.323. Now, often in directions, they're going to tell you how far to go out and for decimal places. Sometimes I go out only 2. This time I just decided to go out 3. With some of the work that you're going to be doing in the future, you might have to go out 4. Okay, so we'll see. Make sure you read the directions carefully. Now, this 1.323 is not our answer. Okay, the answer is they want us to write a function. This is our growth factor, and if you remember anything about growth factors, they have to be bigger than 1, and this is just a little bit bigger than 1. So our equation is going to be y equals. Now this is a lot like, remember when we had to write equations for a line, we had to find our m and our b and then plug them in, and then put back in our x and our y. It's going to be the same thing here, okay? We're going to find our a and plug that back in. They already gave that to us. Then we have all this work we did to find our growth factor. That is our b value. That's why we did that. And then raise it to the x power. Now what's awesome about this equation is that this x power is going to allow us to plug in any amount of hours into this equation, and we should be able to calculate how much bacteria is going to be existing at that point. So if I plug in 4 here, I should get this amount. If I plug in 2, it should be less than that. If I plug in 12, so how much bacteria after 12 hours, I should be able to calculate that. And actually, that is the next question we're asked, okay? How many bacteria cells can be expected in the sample after 12 hours? I'm going to plug a little 12 in right there. So I have y equals 7,500 times 1.323 raised to the 12th power. Now this is just a PEMDAS problem, okay? Y is already alone and positive. I'm going to do exponents and then multiply, divide last, okay? So 1.323 to the 12th. So I'm going to come over here, 1.323, and then I'm going to raise it by pressing this button to the 12th, and I get 27 hot mess. Okay, now I'm going to keep that on my calculator. I just did my exponent. I'm going to now multiply it by my initial amount, which was 7,500. And I get, a big number here, 215,664.862. And that 2 should be rounded up to a 3. So 215,600, I think it was 64.863. And that's bacteria cells. Remember, if we're dealing with a word problem, we should have words in our answers, right? because this number means something. So after 12 hours, that 7,500 becomes 215,000. That is increasing very, very quickly in literally just 12 hours. Okay, that's how exponential functions work, right? It already got kind of big to 23,000 in 4 hours, but then it got ginormous, right? It's getting very, very steep very, very quickly. Okay. So you have one of these in your homework. I'll be honest with you, I know this is going to be probably the hardest problem out of all of them, okay? But the answer's posted, so don't be scared. Let's take a look at one more, and then we'll move on to talking about interest. So a manufacturer distributed 3.2 million aluminum cans in 2005. In 2010, the manufacturer distributed 420,000 cans made from recycled material. Assuming that this rate continues, write an equation. So again, they're telling us to write an equation. They're giving us a before, they're giving us an after, and they did give us a time frame. From 2005 to 2010, our amount of years is 5. Okay? So 3.2 million, and then it became 420,000. It went down. That means we're dealing with an exponential decay function. So right here, this is just a straight up number. 3.2 million is not the straight up number. So we can't just plug in 3.2 equals this times b raised to the 5th. That's not going to work. We need to either change this into the actual number or change this into millions, okay, because it's 420,000. If you want to add literally 5 zeros at the end of this to make this 3,200,000, you could do that. I'm going to actually decide to make this into a decimal. So this is only 0.42 million cans. It's not even a whole million, right? It's only 0.42 million. So I'm going to, now that everything is in terms of millions, I'm going to use the decimals. So I'm going to have 3.2, which is my, oh no, that's what I started with. My goodness, let me erase that. What I ended with should be my y value, right? I'm thinking in my head y equals ab to the x. My end value is 0.42. It went down. Equals my 3.2, which is where I started, times some growth rate raised to the 5 years. Okay, and I know my b looks like a 6 there. Remember, that's a b. So I'm going to start by dividing by 3.2 and divide by 3.2, and that's going to give me a small number. Let's check it out. 0.42 divided by 3.2, 0.13125. So 0.13125 equals b to the 5th. I'm going to 5th root both sides. Those cancel. I'm left with b equals, and then I'm going to take that number I have on my calculator already, and I'm going to press this button and 5th root it. And I get 0.6662, so I'm just going to do 0.666. So my equation is going to be y equals my initial amount, which was 3.2, times 0.666 raised to the x. Now, if you remember, in order for it to be a decay, it has to be greater than 0 but less than 1, and this decimal totally is. So I'm feeling pretty confident about this solution right here. Okay, let's take a quick look and see what we got. Yay, okay, they just rounded this to the 100th place. Again, it didn't tell us where to round it to, so going out 3 places wasn't an issue. The next part of this problem asks us how many cans can be made from recycled aluminum in the year 2050, okay? So if it starts in 2005, what's it going to be in 2050? So our time frame between these two is going to be 45 years. So it's going to be y equals 3.2 times 0.66 to the 45, because 45 years are going to happen. So let's do it. So 0.666 raised to the 45th power equals this number. Now I'm going to times it by 3.2. So I end up with this number. Okay, now this is in millions. So if I really wanted it to be actual numbers of cans, I should go back 6 places. So 1, 2, 3, 4, 5, 6. So that means at that point, I'm only going to have 0.03 of a can. So essentially, 0 cans will be made of recycled material in the year 2050 if it continues at this exponential decay. Now you might be like 0.03 of a can, why don't they just say 0? Well, I want to remind you, this exponential decay has an asymptote, right? And it has an asymptote at 0, okay? It's never going to actually equal 0, but it's going to get closer and closer and closer to it. So their answer was none, because there's going to be no cans. It's going to be 0.03, and you can't have 0.03 of a can. Okay? I know these are tricky. Give a go to the one on your homework. The last section has you looking at this equation, and I do want you to have this equation written down somewhere in your notes. If you end up taking finance, if you already have or you plan to take it in the future, then you will see this function, okay? This is how we do compound interest. So if you see the word compound, then this is usually what they're going to be using. Okay, so let's take a look at what this equation means. The capital A lets you know that that is the amount that you're going to have at the end, which, think about it, if we're thinking of our y equals AB to the x, our end result, our y, was on the other side of the equal sign too. Then we have P is the principal amount invested. The number we're multiplying by in front is where you start. The principal amount means the amount you started with. That's kind of the same thing as A. Then we have 1 plus R over N, where R is our annual interest rate. They'll give that to you. And N is the number of times it can be compounded each year. And we use that both here, and then T is how many years. So it will make sense once we do a handful of these examples. Okay, so let's take a look at the first one where we're going to use this formula. And feel free to reference that formula. Okay, you don't have to have that memorized at this point. So an investment account pays 4.2% annual interest compounded monthly. Okay, and this monthly is going to be important because it's going to help us figure out our end value from here and here. If $2,500 is invested in this account, what will the balance be after 15 years? So we do not know how much is going to be in the account after the years, so we're going to leave that as A. Then we find our principal. What did we initially invest? $2,500. We're going to times that by 1 plus our rate over the amount of times it will be compounded in a year. So you can't compute with percentages. You have to change them to decimals. So I'm going to move that forward 2 spots and add a 0. So 0.042 all over N. Okay, and this N again is how many times it will be compounded in a year. If it's compounded monthly, it's going to happen 12 times a year. And we're going to raise it to the 12 because it's N times T. So they told us it's going to be 15 years. So essentially, folks, this is literally just a PEMDAS problem where we're going to start with our parentheses inside. We're going to raise it to the this times this power. Okay, we're going to multiply those two together. And then after we've done that, we're going to times it by 2,500. So we are going to do most of this on the calculator and then just kind of record the pieces and parts we need to. So we're going to start off with our 0.042, and we're going to divide it by 12. So we get 0.0035, but we're going to add 1 to that right now. So we end up with over here 1.0035 raised to the, and I really should calculate 12 times 15. So 12 times 15, 180. So I'm going to do this part next, and then I'm going to times it by 2,500. So 1.0035. I'm going to raise it to the 180th power. And then I'm going to times it by 2,500. And I get 4,688. And then I want to remind you, we're dealing with money, right? So we want to round to the nearest penny. This is going to get rounded up to 0.87. So 4,688 and 87 cents. 4,688 and 87 cents. That's how much money, if that money just sits in the account, the 2,500, after 15 years, it will almost have doubled. It's not going to be quite double, right? But it's getting up there. Okay, and that's just by letting it sit in account for 15 years. So if you think about that, right, if you were, maybe you get some birthday money for like lots and lots of years, okay, or Maybe you sell something and you make some money, okay? If you invested that in this account and you just didn't touch it, you just let it sit there, in 15 years, you're going to have $4,688.87 instead of $2,500. Now, things change. When you have a better interest rate, you're going to make more money, okay? When it's compounded more frequently or less frequently, that will also change this value. So we have to be really thoughtful about all of those pieces and parts. So let's check out this next problem, and then I'll let you guys get a start on your homework. I know this video is getting long. So find the account balance after 20 years. So this is letting me know this is going to be my T, my time frame. If $100 is placed in an account, so this is where we start, and it pays 1.2% interest compounded twice a month. So that twice a month is going to tell me how many times I need to have my N value outlined. Okay? So let's come down like this. I don't know my outcome. My P value, my principal, is going to be 100 times 1 plus, I'm going to do my rate over my N. So my rate, I can't keep it as a percentage. It has to be a decimal. So 0.012 divided by my N. So if it happens twice a month, so 2 times 12 months in a year is going to be 24. And then I'm going to have it raised to the 24 times how many years? And they said 20 years. So that's a lot of time, and it's going to be compounded a lot of different times also. So I'm going to go back to that calculator, and we're just going to do the same work. Okay, I'm going to do 0.012 divided by 24 and then enter. And I get 0.005. I'm going to add 1 to it. So I get 1.0005. I'm going to raise it to the 24 times 20. 24 times 20, 480. After I raise it to the 480, I'm going to times it by 100 because that's where I started, okay? And this is over 20 years. That's a lot of time. So let's go back. 1.0005 raised to the 480th power. And then I'm going to times it by 100. So that $100 is going to become $127.12. Now you might say, wow, it only gained $27 over 20 years. Well, I want you to think about that for a second. That's a 25% of it. It had a 25% increase over 20 years, and it was only making 1% interest, but it was compounded twice a month. Okay, so yeah, $27 might not seem like a lot. That also wasn't a lot initially invested, but because it was compounded so much, that 1% ended up almost being 27. It was a little bit more than 27% of the original. Okay, so this is how they go about compounding interest. When you read through the word problems, if it says compounded, you need to use this formula. Okay. So, as always, I have office hours. I am going to have my office hours on the 26th like normal. I cannot have them on Wednesday because another class's office hours happen at that time, my honors class. So, feel free to swing by on the 26th from 1 to 2 if you have any questions about this homework assignment. Thank you, folks. We're almost there. A little less than 2 weeks. Perfect. See you later. Bye.